Hello and welcome back. We are talking about section 4.1, exponential functions, continuous compounding, and this video is going to try to tackle exploring the properties of the natural exponential function and examining investments involving continuous compounding of interest. So it's going to all start out with a description of compound interest though. So we say that the future value of some investment if we invest just a lump sum, so a fixed amount of money, we could also talk about annuities, but if we just invest a lump sum P and it's at a fixed annual interest rate R and for T years, and we'll use years as the default time unit in these cases because we like to talk about annual interest rates in general, then the future value of this is how much the account is worth at the end. And then the only extra catch is how often we compound interest. So compound is just a word for compute in this case, how often interest is computed per time interval. So this exponent and the denominator piece k both correspond to the number of times per year that interest gets compounded. So for instance, if it was once per year, k would be 1. If it was quarterly, then k would be 4. Monthly, then k would be 12, and so on. And then this is an interesting sort of case, but if we talk about compounding continuously, then basically what happens is, if we can sort of sneak inside here, this e to the r portion corresponds to this piece of the finite times per year compounding. So compounding continuously is not something that actually can happen physically infinitely many times, but it provides a limit basically for how much compounding more frequently can benefit us. Okay, so what happens is as k goes to infinity, this stuff inside this kind of Oregon-shaped box here goes toward e to the r. So e is this very special number that corresponds to approximately 2.71828. It's often called the natural number. And the E itself is named after Leonhard Euler, whose last name begins with the letter E. So sometimes called Euler's number too. Okay, so computing future value. So we'll look at the Investment Company of America. They suggest that there's a lifetime average rate of return of about 12%. So let's say if we take 250 bucks and figure out how much is this going to be worth after 10 years if we assume this annual rate of return, and if we're going to compound monthly. So remember, this is going to affect that k in our future value. How much is it worth if we do this daily instead? And then finally, what if we compound continuously? Okay, so part A. So future value is going to look like this. Basically, this is the future value setup we're going to use, assuming that it's not compounded continuously, in which case we get that PERT formula, PE to the RT. So this is for some finite number of times per year that interest gets computed. In part A, we have that's 12 times per year because we're compounding monthly. And then just to fill in the other gaps, so the lump sum that we invested was 250 bucks, and then the nominal interest rate is 12%. That's over 10 years, so our future value looks like 250 for our principal, 0.12, so it is important that we convert this to a decimal rather than a percent. K is number of compoundings per year, 12. That appears both in the fraction here and in the exponent, and then 10 years. And that gives us about 825 bucks and some change. Okay, so as we move through here, now we're compounding daily. The only thing that's going to change is that K is 365. So basically, we're going to compare to the number we just got. We're going to look at the 825 bucks and change and say, can we make this better by computing our interest more frequently? If you're really paying attention, there aren't exactly 365 days in a year. The cosmos don't conform to our number system as conveniently as we might like. So you might think of it as 365 point and a quarter, like 365.25, because we have those leap years. But you also might recall that every 100 years we don't get a leap year. Like in the year 2000, there was no leap year where it was supposed to be. And that's to adjust this calendar back to be closer to what the actual cycle around the sun actually is. So 365.24 days is closer. But regardless, the banking industry is perfectly happy with 365. So this equation ought to look exactly like in part A. The lump sum is the same, the interest rate the same, the term of the investment is the same. So really, the 365 days is the only issue that makes this separate from Part A. Okay, so $829 compared to the 825 we had before. So maybe this is the point where we start to see green a little bit. We say, oh look, if we compounded monthly, we made 825 bucks. If we compound daily, we make 829. Could we just make more and more and more money by compounding interest more and more frequently? And this is the kind of thing that probably would have resulted in one person getting rich and then everybody else, and then some sort of institutional rules getting set up to prevent it if that were the case. So since there aren't any rules, then it seems like there's probably some limit to how much this is going to benefit us. So when we look at compounding continuously, that's basically this notion. If we just have infinitely many compoundings per year, then we definitely see an increase in the investment, but the value of the investment at term, but it's not quite as dramatic as we would hope. We can't make infinitely much money by compounding more frequently. Okay, so basically this is the way to get from the finite situation, this whole deal, which is what's sitting in the middle of that future value calculation if k is some real number, and turn it into this part of the PERT formula. So basically, we turned all that stuff in parentheses into this expression as k goes to infinity. So number of compoundings gets larger and larger and larger. This is not something that we would be proving here, but and actually sometimes this is a definition for E. But at any rate, we've got our PERT formula that helps us figure out what this would look like compounding continuously. So the same elements are still there. We've got the same lump sum, the same interest rate, same term of investment. The only thing that's different is we're using this PERT formula. So notice it doesn't have any k's in it anymore because the assumption is that k is going to infinity. So it's actually an easier calculation. And so what we see is not terribly impressive 830 bucks, whereas we were making $829 and I think 87 cents when we compounded daily. So moving to infinitely many compoundings got us, not quite 30 more cents. So the moral there is, sure, we can make more money, but this is the cap. So this is the best that we can do with a 12% interest rate, just based on changing how frequently we compound. So the other half of this, present value, basically just says solve for the principal when you know the final value. So if you know the future value of this investment and you'd like to find out what it's worth right now, then we can use one of these formulas. I'm going to do an example using the formula, but the truth is we really don't need this. If I go back to our future value formula, then really all we need to do is take this formula and know what B is and know all this other stuff and figure out what principal is. So if we're really interested in making the most use of our brain space, there's really not a reason to memorize or even include on a note card the present value formula, because we can always just take this equation and solve it for principal. Okay, so in the interest of having fewer things stuck in our brain space, then maybe we can get away with not memorizing this present value calculation. But nevertheless, it's there. It's just a formalization of how to solve for principal in that other equation. Okay, so this retirement account is supposed to have $1 million in it, and that's in order just to fund his retirement out of this, some sort of annuity that payout annuity. And he's 30 years old now. He'd like to have this $1 million in there by the time he's 67, and we'll assume the interest rate is about 3.6%. This is also based on some American funds details. So we'll assume a quarterly compounding, just whatever. Could be just about anything. And then the question is, what lump sum would you need to invest now? So here are some key phrases. Whenever we're talking about a value now as opposed to some value in the future, then we may be thinking about a present value kind of computation. Okay, so we could use the formula that we were given. Here's the final balance, and this is the principal, so we would be solving for this initial investment, or we could just break out the present value formula. But in either case, the constants actually match up. So remember that he's 30 right now, and he's looking to retire when he's 67, maybe to get Social Security, full benefits, etc. So that's a difference of 37 years. So that's the term of this investment. Then the nominal annual rate that we were given was 3.6%, and then compounded, so quarterly, so 4 times per year. And then the goal is an output of $1 million. So this is actually the B portion of either one of these equations. Okay, so this is using the present value formula. But again, we don't actually have to use this if we don't want to. So here is B, the final value that we'd like to end up with, and then the usual culprits. So we've got R, we've got K, since we weren't compounding continuously, and then the term of the investment, the big T. Okay, so all this amounts to about 265,000 and a half. And so rounding up, I guess that's to be safe, so he's not like 12 cents short of his full vested amount for the payout annuity. Just to be careful, we'll round up to the next cent. And then basically, just to put this in words, Alan would need to have this much money invested at the 3.6% interest rate compounded quarterly and let that sit for the next 37 years in order to reach his retirement goal of $1 million. So this is the present value of this future $1 million. Okay, one other topic for this section. So I keep using this, and I haven't made a big deal about it yet, but I keep using this phrase nominal interest rate for these other values. And the nominal interest rate, because if we look back, this 3.6% that Alan was using, he doesn't actually make 3.6% per year. He makes something better than that because the interest is getting calculated more and more. The phrase compound interest is all about this interest upon interest. So since it gets computed 4 times per year, he's actually making a better rate than 3.6%. In other words, if he started out with $100, he'd have more than $103.60 at the end of a year because of this compound interest. So the effective interest rate is an effort to figure out what does this interest rate look like if we actually considered how much would or how much would an investment grow over the course of 1 year in actuality. So we're using I, we could use R, but just to avoid confusion. So the nominal rate is R, and this I is sometimes called the periodic rate. But so what we really have here is R over K. And so basically this looks like the growth factor for compound interest. That 1 plus R over K to the K looks like 1 year worth of growth in some investment. So this is our growth factor, which is great. This is going to be 1 point something or other. And then we take away 1 in order to subtract off that 100% and see just what is the rate of growth. So if it was 1.01, then we'd be down to 0.1 as our effective interest rate. And then for continuous compounding, it's the exact same deal. This is the growth factor when we compound infinitely many times. So we're still figuring out, that's the ER part of the PERT formula. So we would just extract that piece off, take -1, and then that would give us the actual rate of return on this investment. So let's try this out with Alan's retirement account. So it doesn't actually matter. The term of the investment's not interesting because the effective interest rate is only interested in 1 year worth of growth anyway. So it's saying by what percent would it actually grow each year. So since it was 3.6% compounded quarterly, that's actually all the information we need. So the effective annual interest rate would look like that nice formula. It was computed for a finite number of times, so not the ER formula. We're using 1 plus R over K to the K. And then plug in the specifics. We know the nominal interest rate was 3.6%. It was compounded quarterly, and then a calculator can help get us some approximate value here. So the final answer is 0.03649. And then a conclusion in words to go along with that is that this number is slightly larger than 3.6%. It's not hugely larger, but out in the hundreds column of percentage. So basically he was actually seeing growth of about 3.65% every year, whereas the nominal interest rate was only this 3.6% part. So the beauty of compounding 4 times per year was that he got an extra 0.05% on his investment every year that went by. That's it for section 4.1. We'll see you soon for section 4.2.